Welcome to the first content video of PIC 16A. So in this video, we'll discuss numbers and variables in Python. We'll introduce some simple ways in which we can operate on numbers. Like we'll discuss how Python represents numbers. We'll discuss ways we can combine numbers to get new numbers. And we'll also discuss assigning variables and some of the ways in which we can compare variables and use them in computations. So in this lecture video, as in all lecture videos, I really encourage you to open up a blank notebook and actually try typing the code with me, running the code as we go, exploring a little along the way, trying out a few things so that you'll really get the feel for writing this kind of code. So please open up a blank notebook and try to follow along with me. I hope we won't go too fast. So Python is an interactive language. It's interpreted rather than compiled, as we discussed previously. And this means, among other things, that Python is a very practical substitute for a calculator. So let's try a few simple computations as examples. The easiest way to do a computation in Python is just to type in what you'd like to compute in a very similar way to as you might in, say, the Chrome search bar or something like that. So here I'm going to add 27 plus 6, and when I hit Shift Enter, that's Shift Return, I have Python perform the computation and show me the answer as output, so I get 33. Looks pretty good. Okay, next I can do other kinds of computations, and I can use parentheses to group computations together. So here I'll do 3 times 2 plus 3, and I get out 15, looks fine. The parentheses, just like in regular written mathematics, the parentheses tell Python the correct order of operations in which to perform computations. Things within the parentheses will be computed first. So next, we can also do division. So if I do 36 divided by 12, I get 33.0. So there's something a little bit interesting about this result. So 36 divided by 12 is just 3. And so Python could represent this answer as an integer. However, you'll notice that there is there's a decimal place, 3.0 in the answer. Python has represented this answer as a floating point number. Because in general, division can produce decimals. So here's an example of division producing a decimal. If I did 35 divided by 12, here's a floating point number where I really need the decimal place. Because this is possible, Python will always give you a decimal number, floating point number, when we do division, even when the answer can be represented exactly as an integer. We can also do things like computing the remainder after division. So if I compute the remainder of 37 after division by 12, I'll get 1 because 12 exactly divides 36, and 37 is 1 more than that. Similarly, additionally, I can do powers. I can do exponentiation, where these two asterisk signs mean raised to the power of. So I do 2 asterisk asterisk 3 means 2 to the power of 3. And I'll get 8. Great. So most of these operations also work with floating point numbers. However, there are a few surprises that are possible. So here's a place where we won't be surprised. If I do 27.3 plus 5.4, I'll get a reasonable looking floating point answer. No problem there, 32.7. If I do powers, so here's 3.2 raised to the power of 2.3 with those double asterisks, I'll get a floating point number that's about 14.5. So that works fine. Here's something that's a little bit unusual. So if we do 37.4 and we compute the remainder after division by 12.2, now you can take out a pencil and paper and check that this answer is 0.8 exactly. What Python actually returns to us, though, is 0.8 followed by quite a lot of zeros, and there's a little 7 hanging out at the end. Now, why is that little 7 there? It doesn't come from the mathematical truth of this computation. It comes from the fact that Python represents its real numbers, its floating point numbers, using finite precision floating point representation. And this means that most numbers cannot be represented exactly using floats in Python without further work. So we have a finite precision representation of the answer of this computation. The chosen answer that Python has given us is very, very close to 0.8, and it's as close as it can get in finite precision to the correct answer. So keep in mind that what you get in Python might not exactly correspond to your mathematical expectations. It will be epsilon close to your mathematical expectations when using finite precision arithmetic. Okay, let's see another example of this. So suppose I'd like to compute the square root of -1. So this should be I, the mathematical square root of -1. And here's something kind of interesting that happens. So if we do -1 asterisk asterisk to the 0.5 power, using parentheses to make clear the order of operations, I can observe that I see a 6 point followed by a bunch of decimals raised to times 10 raised to the -17th power. So I get a very small number that's machine indistinguishable from 0. That's a floating point representation of 0, plus 1j. So Python uses j to refer to the square root of -1. That's the engineer's convention rather than the mathematician's convention. So here we have the computation of a complex number that Python represents using floating point arithmetic. And we can see the representation of the imaginary axis using this letter j. So that's a quick overview of using Python as a calculator. There are a few things to keep track of related to finite precision arithmetic, but overall this is pretty straightforward and should be in some ways familiar from your experience in C++. So now let's practice assigning variables. So when we're writing code, it's always a good idea to give names to important numbers or strings or data structures. So let's try an example of this. So I'm going to do x equals 2.73 and then y equals 5.4. This single equal sign allows me to assign variables to values. And then when I do x plus y, that's exactly the same as writing 27.3 plus 5.4. So I can do the same computation that way. Now, of course, I can also assign variables to the outputs of computations. So let's say I want to have z be equal to the output of x plus y. I can check that z, I get the same 32.7 that I would have gotten just checking the output of x plus y directly. So I can assign variables, I can give them values, and then I can give new variables the values that I get by combining old variables using mathematical operations. So this should all feel pretty familiar as well. Now, an important question when writing code is, when are two variables the same? Okay, so there are two ways in which variables might be considered to be the same. So here's an example. So I'll do x equals 4, and I'll do y equals 4. And the first thing we can check is whether x and y have the same value. And we can check that using this double equal sign. So x double equals y. And that'll check, hey, do these variables have the same value? And I can check that that is indeed true. X double equals y is true. These variables have the same value. Now, there's a subtlety here because there's a different important way in which variables can be the same. And so we can ask, do x and y refer to the same object in computer memory? Are these actually pointing to the same place? And we can check that using the ID function. So if I check for the ID of x, I'll get a number. That number is a signpost to actually what x refers to in computer memory. And I can compare it to the ID of y, and I can see that these are actually pointing to the same location in memory. So not only do x and y have the same value, they actually point to the same data on my computer. And we can check that further using the is operator. So if I do x is y, do these two variables literally point to the same location in my computer? I'll see that the answer is yes. They do literally point to the same location in my computer memory. Now, one thing that's interesting here is that we didn't actually assign x equals y, we assigned them separately, x equals 4 and y equals 4. Python is actually storing the number 4 in a location in computer memory, and then when we construct x and y, it'll automatically construct these as pointers to that same number 4. This won't always work, so we'll see later examples where when we do x and y, we initialize them separately, but to the same value, we'll find that they are not identical. But in this case, they are identical and point to the same location in computer memory. So an example where we'll see something different happening is when we look at lists. So lists are mutable, they can be changed, unlike integers and floats. Because lists can be changed, two lists do not point to the same location in memory, and we'll see an example here. So here's an example of a list. You don't have to worry about what this is at the moment. We'll talk about that in a later lecture. I've assigned A equals the list that's 1 followed by 2. B equals another list that's also 1 followed by 2. So these are just a collection of 2 numbers. A and B are both collections that just consist of 1 followed by 2. Then I'll also initialize C equals A. Okay, so in the integer case, we saw that when we initialized 2 variables and gave them the same value, they ended up pointing to the same location in memory. However, that's not going to be the case here. So if I run id of A and id of B, I'll see that I get 2 different numbers, indicating that A and B point to different places. Okay, so A and B have the same data, the same value, but they point to different places in computer memory. So with that in mind, take a moment to predict the output of the following code. My first test is A is B, and my second test is A equals B. So take a moment and see and think about what will happen when we run this code. Okay, so because A and B point to different locations in computer memory, it's not the case that A is B. That test will be false. On the other hand, they have the same value. They both are lists that consist of 1 followed by 2, and so they are equal. So when we check this, we'll see the first test is false and the second test is true. On the other hand, because we said that C is equal to A, that will cause C to have the same ID as A. It will point to the same location in memory. You can compare this to A above, and so we can check that A is C is in fact true. So there are subtle distinctions between 2 variables having the same value, being equal in the sense of having the same value, and pointing to the same object, actually being literally the same thing. So usually in this course, this distinction will not be extremely important. We'll usually care about equality in value rather than identity. But it's an important point to keep in mind when writing code, as this can sometimes have unexpected consequences. So we'll be on the lookout for these going forward. So thanks for joining this video on numbers and variables. In the next video, we'll move on to strings.